Okay, everybody, welcome to this session about IPv6. Let's start with a quick introduction. My name is Rolf Leutert from Switzerland, running a small company dedicated to protocol analyzing and troubleshooting. I do nothing else, just this, and I like it and I love it. And I'm pleased to give you here an introduction to IPv6. It's around long time ago, so it's nothing really new, but to my experience, many companies hesitated so far to implement it, or they did not have the need to implement it. So it's still an interesting topic, and as long as you don't have the pressure to implement, then you can wait, but one day there will be no way around it. IPv4 will still be here for a long time, but more and more applications will ask for IPv6. There are already applications out there which require IPv6. So one day you will come into contact, and that's why I think it's worth to have a look into it. It's quite different, not only the address. You may think, okay, it's just replacing an IP address, which is 4 times longer, but this is not true. It's actually much more, which we are going to see in this presentation. A lot of processes are new, so it really helps to understand this. So it's amazing what step is made here in the number of addresses available. That was actually the key driver for it. You have heard and learned that the IPv4 range has run out around the world. They are not available anymore. You still can use it in your private local area, of course, and then convert and translate to IPv6 or whatever, but there are no public addresses available anymore. You would think that doubling the address space or 10 times would be good enough, but they increased it by a real big step. Remember, we are doing from 32 bits to 128, and every bit doubles the space. So we have 96 times doubling the present space of 4.2 billion addresses. So this gives an unimaginable number of addresses per person on the planet. It seems like they wanted to solve this problem once and forever. The disadvantage is we have a very unreadable, clumsy address. I don't want to type this, or I don't want to give this over the phone to another person. This is very easy with 5v4, but this is very unhandy with IPv6. That's the disadvantage. The advantage is we will never have a room address problem anymore. You can make huge networks with thousands of or 100,000 of addresses. One thing has become easier. That's the subnet mask network identifier. If you look at an IP4 address, you cannot say what is the network and what is the host. You can assume it's a class 24, class C, but that's not true anymore since we have variable subnet masking. So you need a slash and the subnet mask identifier. This is not true anymore with the IPv6. With IPv6, it's defined that the 64 first bits are the network plus the subnet. So here are the subnets. And the rest is the interface or host ID, how it was before. So you have an unimaginable number of hosts available in a subnet. You will never going to use it. One good thing is that's not the way you always have to note the address. There is a much easier way. You can get rid of the leading zeros. For example, here, zero, the leading zeros, you can get rid of it. And if you have a number of consecutive zeros, You can get rid of them all by the double column here. And this is the same address. So you just need to fill in the zeros here in the middle up to the 128 bits. So that's really an advantage, and Wireshark makes use of this notation, of course. We will see in a minute that Wireshark knows these rules of skipping leading zeros. I just made a small little example to show you how unimaginable the number of addresses are which we get. Remember again, with IPv4 we have 4.2 billion addresses. Don't mix up billion from Europe to the States. In Europe we have also billion, but that's 1,000 times more. We say these are millions, milliarden addresses, and milliarden we say instead of billion. So this is confusing sometimes. Okay, let's assume you press the today number of IPv4 address on 1 square millimeter. You just concentrate it on this small little part. And now then you roll out a flat which corresponds to the IPv6 area. This gives a little bit a view, a picture, how unimaginable big the range is. You would say it's maybe a football field, or it may be a country, or it may be whatever. It's measured in world surfaces. Unbelievable. We are ending up in 155 millions of Earth surfaces with every square millimeter covered with today's IP address. Really, that's a huge space. It will solve our future addressing problem once for all. Okay, let's just go into the details because we have limited time in this hour here, and I would like to give you as much as information as possible. Yes, we are all Wireshark people. We are all interested in bits and bytes and in headers. So I made a direct comparison here. What's new, what's old, what's lost, and so on. So let's start comparing with what we know. We know the IPv4 header with the version 4-bit here at the very beginning. Of course, we still have this, but of course, we have a number 6 in here. We don't have the header length anymore, which has gone because the base header in IPv6 always is 40 bytes. In IPv6, you could have options, so you have to have a header length. So that's gone. We can save 4 bits with that. The diffserv field, still there, still the same coding. It's 1 byte, but it's renamed to traffic class. But it's still the same coding. So it's taken over 1 to 1. Then we have a new field, the flow label. It's 20 bits, and it's quite difficult to understand what it's for, but I can shortly describe what's the idea behind it. The idea behind it is that we mark a certain flow of data with a unique number. And this would allow that the routers in the core do not have to look into the routing table. They just take the flow label from the first packet, compare it with the routing, and then mark the flow, use the flow label on the following frames. So this more a switching than a routing then. This is comparable best, in my opinion, to MPLS. In MPLS, you also add a layer, a header, a tag right after the Ethernet. And then in the core, all the MPLS router are using this flow, this MPLS label to forward the packet. I did not see any implementation yet, but maybe there are some days, or I didn't see them, but it's a nice idea. The difference here is this flow label would be provided by the client, by the sender already. MPLS is provided by the edge, by the first edge router, and removed by the egress router. This would not be the case here. So the client, which decides for a long file transfer with a lot of frame, may add this field right from the beginning. quite an interesting feature. Go Google if you are interested in that more, but again, I did not see it implemented yet. It of course would need implementation on the router. It would need implementation on the clients and so on. And this would take a while. Payload length, nothing different. We have a length field. We don't have the identification flag and fragment offset anymore. Why? We do not fragment anymore on IPv6 router. IPv6 router will not fragment anymore. That's very big difference. The reason is fragmentation on a router takes a lot of resources. It has to split packet, have to copy the IP header to all the packet, have to calculate the offset and everything. IP6 router will have a lot of work to route this million or thousand of addresses. So the routing table will explode if we do not summarize correctly. So let the router do their job and do not bother them with unnecessary work. So we need MTU discovery this time. I have an example with that. The client sends, if the client sends 2 large frames, they come back, a message comes back, and then you have to fragment on the client. So a very big difference here. We save 32 bits again, which fall away. I will miss that one really hardly, because if you look at the client going out, each packet increases the identification. So you can easily then use this field in IPv4 to differentiate between a retransmission of TCP and between a frame which is somewhere doubled on a switch, because a retransmission in TCP will have a new IP identification. Of course, a doubled frame from a switch or whatever, which happens from time to time, will have the same. So I will hardly miss this ID number for troubleshooting, but it's not needed anymore because the main reason for it was fragmentation. TTL, time to live. I love this field too. You will see it in all my profiles because you can see how many hops a packet has crossed already. I will show this. It's renamed to hop count. It's still the same value. It's 1 byte, goes up to 255. So that's the same. The next field is different. Remember, in the IP header, we have a number indicating for what's following after the IP header. Number 6 means TCP. Number 1 means ICMP, and so on. We have this one exchanged or extended because we have IP headers which can follow IP headers, so-called extender header, extension header. We still have a number 6 in here if the next header is a TCP, but we will see on the next page, we have the concept of modular headers here, which is again new comparing to IP version 4. We don't have the header checksum, which is turned off anyway a lot of times, not used anymore. It's useless because we have a checksum over the frame, the Ethernet checksum. When IPv4 was invented, IPv4 was not necessarily transported over Ethernet, so they provided an additional checksum for safety, so this is gone. So we save some bits, but of course, these bits and bytes will be used by our address, which is 4 times longer. So our base header is 40 bytes already, which of course then takes room for from the payload. If you do not use jumbo frames, then the payload is reduced by this 20 bytes. Okay, we have to live with that. On the other hand, on the other side, we had this option field, which was very rarely used, but still it was available for source routing and things like this. I hardly ever saw it, but in IPv6, we have a different concept. You can add different headers, and we'll see on the next page what extension headers exist today. So we have a very modular header system. We can do extensions in the future. whatever. So this protocol will be very scalable for whatever requirement will come up in the next developments. Okay, let's talk about this header structure, which again is completely different from IPv4. So this is similar to an IPv4. We have the IP header, and then we have the number 6 here for TCP, so that the receiver knows after the header is finished, we have to decode with a TCP RFC. So this is still valid, is still the same. But as I mentioned, the next router, the next header could be an extension header which carries more IPv6 information. For example, a routing header, special information for router, for example, for tunneling or mobility or whatever. So the number 6 is moved to the routing header. Of course, in the routing header, we again have a next header field. And here we have the new number for the routing header. Every new extension header has its own number. And the point is, this can be extended more or less unlimited. Of course, the limit is the frame size. There's less and less room for the TCP data then. And it is even allowed under certain special circumstances that the same header appears twice. It can make sense. So it's really very flexible. That's should cover all our needs. So let's go on. Here are some extension header which exists today. For example, that one is an interesting one. I can add a hop by hop header, and this header must be read by all routers on the way to the target. So this is brand new. A router normally does not read into the payload or into the header. The router normally looks at the IP address and then forwards a packet. So if you want to provide information for a router, you have to send the packet to the router. This is new. On a first frame to your destination, you can add a hop by hop header and ask all the routers to write their MTU size into this frame. So you find out what is the MTU size on this pass and a lot of other possibilities. Of course, this is not just fine and good. What if this is not properly implemented and what it has errors and you can bring down all the routers on your way to the destination? It's much easier this way than it was before. So this, of course, all these new features always carry some risk that they are not properly implemented or that they're not properly used and so on. But that's something which has to be solved. Okay, so here, for example, an extension header. I go back. That's the fragmentation header. So fragmentation, again, fragmentation has to be done on the sender. So what I did here, I sent an ISIM ping, which was too big. And then the router sends back a packet too big. We know this existed on v4 already. And it tells us what packet size to use. And then you see that the client starts fragmenting. So we then have the original header and a fragment header part. So this belongs together. So this could be multiple parts, of course. Here is just one part. And that's nice that you can add here a column with the next header. Here you see the hop limit, which I mentioned. 128 means this is coming from a from a Windows PC, and it has not crossed a router already. 128 is the default start value for Windows. If it's 64, it's the default value for Unix systems Mac OSs and so on. So I always can say where was Wireshark placed. So Wireshark was placed in the same subnet as the sender. Otherwise, we would see here a hop limit lower than this value. Let's look at address configuration. We have to learn new things, of course, and new terms and new numbers, and that's the hard thing about IPv6. Everybody knows that the 10 address is a private address and so on, and these numbers are all gone. They are still there, the function, but they are gone. They look completely different. But I tell you the most important values. And I have placed you a quick reference card in the Zoom 1, the PDF. We have a lot of new information, and I summarized this on a quick reference card. So you cannot learn this all in 1 hour. So I just made a collection of the most important stuff. So what you see here on the screen is more or less in a concentrated form on the quick reference card. So all public addresses start with a 2 at the beginning. At the moment, we are only using the 2 addresses. We have such a huge range. There will be 2 for a long time. So let's go back a little bit. And then you see this is a public address here. Starts with 2 and then the prefix and so on. Starts with 2 and whatever. So these are public addresses. Then we have one important, there is a special range only for documentation prepared. So if you want to do some lab, isolated lab, you can use this range. It will not be routed on the internet. And if you don't want to publish your IP address on a documentation, that DB8 is reserved for documentation only. It's really amazing. We have so much address, we can reserve one only for documentation. This avoids that people take your documentation and type the address in, like a lot of people do from examples. That's won't work here. One other important address is the FE80. You will see this address a lot. FE80 is a link local address. And as soon as you have IPv6 enabled on your route, on your PC, an FE80 address is selected automatically. So let's quickly change to Wireshark. Hope this works here. And if you hover over the different address, you always see an FE80 address. Even if you don't have a public one, you have an FE80 address. Every adapter has an FE80 address, even if it doesn't have a public address. The FE80 address is only link local. It's not routed. You can only use it in the subnet. That's also a different new approach. We used in IPv4 the same address in the local subnet as well in connection to foreign. A new idea. So you actually can ping with this address from the very moment you have the FE80, you can ping with this address. Then we still have what has been called private address in IPv4. They are not called private anymore. They are called unique local address. And there are 2 groups, but more or less the FC has not been implemented because no authority wanted to take over the administration. So what you recommend to use if you would like to use a local address, then use the FD and then you can use all the rest. If you want to have a unique FD address, you can even use this kind of generator here, and you just enter any of your MAC address and you get a unique FD prefix. What is the purpose of it for a private address? Yes, many times these days, you notice every company is using 10 addresses for their local, for their private addresses. once you try to merge companies which both use 10 address, it won't work because then you have address overlapping. In order to avoid this, they provided a system to create a unique local private address. And then if you start merging, those companies will have FD addresses, non-routable on the internet, but they will not conflict with each other. Another important role plays the multicast address, also on my page. A very new, again, a brand new approach here, which we are going to see. Within the multicast, you can address the scope, the reachability, and the function. We are going to look at this in a minute. Anycast address are still there. There are unicast addresses used by multiple hosts, for example, the root servers, very special application, which we don't cover here. We have special addresses again, the loopback, the zero address. The zero address looks nice. It's just two columns because it's all zero. And if you use the shortened rule, it left over. That's what we see in Wireshark. This is a nice too. Make a ping on column 1, and you ping your local loopback. That's the 127.0.0.1, which we had in IPv4. So some things have become easier, but most of them have become complexer. This is a very important message. We don't have broadcast anymore. The FFF in the MAC address is not allowed anymore. We would like to reduce broadcasts. Broadcasts are a pain for large networks. They make an interrupt on all the adapters. How can we still provide information on the network for all of them? We are going to see this. On the layer 3 also, they do not exist anymore. Remember the 255 in the IP address? It does not exist, it's not allowed. So quite some changes here in this part. Okay, now you see a mix of addresses here, FE80, local addresses. You see the column, the zero address here, and you see 2000 address. So you really have to get used to this. And then you see broadcasts here. Sorry, multicast, not broadcast, of course. The FF02. If you go to my QUIC reference card, you can find out the FF02 is a link local multicast. So it will not leave your subnet. So the 02 here indicates the so-called scope, the reachability. If it says FF05, it is a site local multicast, stays in your subnet. So really much more flexible than we had it with the 224 addresses, 236 addresses in IPv4. We can, as a sender, we can define the reachability of a multicast. And then this comes into a play here. Also on my QUIC reference, the 01 means all nodes, the 02 means all routers, and so on. So the last host, the so-called ID, is a long list. My QUIC reference is not complete here. If you find anyone not on the list, you can easily Google for it. So this address defines for which function this frame, this multicast is intended to. So if the client is looking for a router, which we are going to look right in a minute in more detail, then it sends a router solicitation to the FF02 address. So this is much more specific than just sending a broadcast to everyone, because these multicast addresses can be filtered on the Ethernet adapter. The Ethernet adapter knows which multicast addresses apply for him. And if an address comes in for number 2, which is a router, this packet is discarded on the Ethernet level. It does not produce any interrupt. It's much more efficient in processing. Okay, we'll come back to this, but we have to look at address configuration. Again, a completely different approach. The FE80 address, for example, which we just saw, is created on its own. And we have two different systems to create it. One is derived from the MAC address. So it takes part of the address and puts it in a strange matter here with the fixed FFFE in the middle. And the other way is just random. Select an address random generator. Of course, this address has to be verified on the internet, on the local net. It's only local, which will be done. Both addresses will be verified anyway. So if it's an AUE or if it's a privacy, the privacy by now is default format for all operating system. They started most with the AUE. But today it's privacy. On the back side of my card, you can see the commands to switch from privacy to random and so on. If you want to change this, let's go back to my screenshot here, and then you can see here, this seems to be a random address because the FFFE is not available here. So here you see the FFFE. So this is a hardware derived address. So you can easily see the difference here, but it doesn't actually matter for the function, but just that you learn. So let's go back one. Every adapter has an FE80 address, but with this address, you cannot communicate outside your local subnet. So it's not really very helpful. So you also need a public address. And these are different ways now of getting a public prefix. The most frequent way which we are going to see is getting this prefix from the router. Again, that is completely different from IPv4. In IPv4, the router does not supply with a prefix. It's either you manual or through DHCP. This is completely different. We are going to look at in a minute. Again, the 2000 address, the public one, can also be AUE derived or MAC derived, or again, it's today default is random. Again, it has to be verified on the network. We are going to see this in a minute. Okay. Most components, network components these days are dual stack. So there is no excuse anymore not to use IPv6. All the firewall, all the routers, all the servers today are dual stack, even the clients. And this looks like this, that they have all more or less in double. And the differentiator is in the type field of the Ethernet. It says it's an IPv4 or an IPv6. So we have a different type field in the Ethernet. I can quickly show you here on the trace file. If you go to the Ethernet, then we see we have type field 868DD. And remember in IPv4, it was 800. So even already on the Ethernet card, information is available where to forward the frame. TCP and UDP is still the same. That's the idea of this stacking, of course. We have not to change anything on that part. We don't have the ARP anymore because ARP is using broadcast. So how do we resolve addresses? We are using ICMP version 6. So it's one layer higher. Before the address was resolved here between 2 and 3. Now it's on ICMP on top of IP So a lot of functions have been moved to IPv6, which we are going to see right on this slide. So IPv6 plays an important role. Again, you see a lot of ICMP6 here. So it has much more functionality than, than in the IPv4. We are not looking at this one here. These are the ones you know already from IPv4. But we have new ones. We are going to look at these ones. We are not going to look at these ones, but just to inform you, IPv6 will also replace the IGMP, the multicast protocol. It's done via ICMP with these multicast messages here. So IGMP is not used anymore in IPv6. But we are going to focus on that one here. That's what is most probably used. I told you already, one of the big differences, the router can provide us with a lot of information. And it's brand new that the starting client is looking for a router. One of the first frame going out is looking for a router. This is the router multicast. Of course, a local, it will not cross the router, doesn't make sense. A router has to be in our local network. And then a router will probably respond, hopefully, if there is a V6 router configured with an advertisement. So we have solicitation, search messages, request messages, and we have advertisement. And in the advertisement, you see all the necessary parameters for, let's say, a normal workstation. We see the prefix /64. The rest can be either derived to AUE or can be random, depends on the workstation. We have the DNS. By the way, if the DNS is local, you only get the FE80 address. The MTU size, that's a nice thing to avoid MTU problems. And you can even, yes, we have all parameters now. Prefix, subnet mask, default gateway, and DNS. That means a normal, let's say a normal client like a PC or an IoT device or whatever is fully configurable from the router. Of course, this is stateless. We don't have a register. We don't have a list of which addresses. And you may still want to have a list of your workstation. And I'm going to show you that this is still possible. But this is a way of providing hundreds of devices with an address which you do not want to care about. And that's new. We do not even need a DHCP server for this. And this is really nice and opens up a lot of possibilities. So after this configuration, a client has different addresses. It has an FE80 address here. And in this case, it has a public address. And many operating systems like Windows, they also create a second temporary address. They have a fixed address and one or more temporary. So this address is going to be changed from time to time. This is a little bit confusing. You may have up to 5, 6 addresses, and they will not be used for long, but they will still be there, just the frame receives back. But one address is fixed for all the time here. That's the fixed one here. Then you have the default gateway and you have the DNS server. If you look at this configuration, you see this strange little percent and number at the end. This does not belong to the address. It's called the so-called zone ID. Let's have a look. What is the zone ID? The zone ID is used because we have FE80 interfaces. We have an FE80 addresses on all interfaces. So if we want to ping another FE80 station, we must tell which interface we are going to use. So if you ping another FE80 address, you have to look which interface you would like to use. Would you like to use the Ethernet, or would you like to use the wireless? And then you should, at the end of the address, you have to add the percent of this zone ID. So that's, again, it's quite different. But this is because we have a local address. Of course, you can always ping a station with the public address, and then you don't need the percent because the public address is assigned to a specific interface. Now, let's talk about how you can control the behavior of a workstation. That's, again, a really very good feature for people responsible for network. We have much more control over the behavior of the workstation, except you configure it manually. This is still possible, which is not on this list. If you want to configure manually on the notebook for PC, whatever reason, it's up to you. But if you want to configure automatically, then you had so far only one choice, via DHCP. And now you still can do it via DHCP. You still can do open a range, and you can still let the client register with its ID. That's all good and still there. Don't panic, because we just got 2 new options, but the old stuff is still there. So what is the difference here? The difference here, this is called stateless configuration. We do not register which device has which address. This is stateful. We have to create a range and can see which address is assigned to which station. In the router advertisement, we have a lot of information, and 2 flags are quite nice for management. We have the other flag and the management flag. If both are set to 0, I'm telling the client, take all the parameters from my announcements, the 4 parameters which we just see. IP address, mask, default gateway, DNS. And that's it for IoT. Good enough. No problem. No DHCP required. We can go one step further. Let's say you have an IP phone. IP phone may ask for more parameters, like TFTP server or whatever. These are not provided by the router so far. So you can tell the client, use for the interface identifier and for the prefix, use what the router is giving you. And for the default gateway and all this stuff. If you need more parameter, you are allowed to come to search for a DHCP server. So that's kind of mixed. It's still stateless. The DHCP server then provides options without registering the client. And then we have the full manageable version. So we have a nice version, selection of version of choice, what we would like to do. And on the router, yes, you see this here in the Wireshark, of course, the management bit and the other bit are set here. On the router, I have 2 screenshots here, how you do configure it, and the neighbor discovery, other config flag, management, so on. And here you are on a cycle router. You even can do it with a selection. If a client receives the other bit, then it will send out another request to a DHCP. Again, if you look on the card, it's a 1, 2, 1. Don't mix it up with the 12. It's a 1, column 2. 1, column 2 is all DHCP relay agent. Of course, it's a local multicast because the router has to pick it up, similar like in IPv4. You see this. Neighbor discovery. Neighbor discovery again is completely different because we do not have the ARP anymore. How do we do neighbor discovery? And here is the most demanding part of IPv6 addressing. It's called the SNMA. How do I search for a MAC address of a neighbor? I do not have broadcast anymore. I do not use the FF02 column 1, which would mean all node. Then I would have the broadcast back. What I do is following. Every station on the startup forms an additional address. So in addition to the FE80, which we already have, and to a possible global address, which we already have, we form another own address, a personal address for our own. And it has a long mask. It always starts with this. And we take the last 4 bytes from our address into this. And that's our personal multicast address. And if somebody is looking for us, searching for us, he does the same. If another guy wants our MAC address and only has our IP address, he takes our IP address, takes the last 4 bytes, last 3 bytes, and form the SNMA and sends out a neighbor discovery to this address. Really strange process in order to avoid multicast. So let's look at the trace file to see how this looks. The first thing is, when you start up a PC, it verifies that its own address is unique on the network. So again, it's very quick to learn all this pattern, but this is a SNMA address. You see the FF012, 01, FFF, and so on, all very quick. And this is kind of duplicate address test at the very beginning. Then it's looking for a router. And then it's looking for a neighbor. Here is a neighbor discovery. I'm looking for the MAC address of the router. Here is the MAC address of the router. And I need to have, is the IP address. I need to have the MAC address of the router. So I send out a neighbor solicitation and come back a neighbor advertisement. And in this neighbor advertisement, we will have the MAC address of the router. So it's no ARP anymore, neighbor solicitation, neighbor advertisement. But the difference is this address here, it's not a layer 2 broadcast like we had it on the ARP. It's the SNMA address of the target which we are looking. Really strange. You may need some additional time to study this. Of course, we also have kind of ARP table. It's not called ARP table anymore. It's called, of course, neighbor table, which you can open up with this command. Okay, little hurry in a bit, of course, with all this stuff. Any questions so far? What if in step 1 a duplicate address is detected? Okay, yes, that's a good question. I would have to test myself. Let's go back here. What in page 27? Yes. What if a duplicate is detected? It would reply, of course, with a neighbor advertisement with this ID. And then it depends what the client is going to do. This is, I don't know, I never saw it. If it's a fixed address, like FFFE, it cannot just take a new one, right? Because the client is configured to have the hardware address. But then the chances are very slow that we have duplicate IP address, because the MAC address has to be unique too. If it's a random address, I guess it's just dicing and taking another random. But I would have to check that. But would take some work to simulate that. If it's a random, it's no problem. It just takes another random. And if it's the hardware, the problem should not happen, because if it's hardware, the hardware has to be unique in the subnet. Okay. What is the command line command to show the table? Okay. The neighbor table, you mean? This one? This is for one interface only. You have to enter again the interface number if you want to see for one interface. You can leave this off and then it shows all found neighbors. Let's talk about MAC address. Yes, I forgot. Let's talk about MAC address. That's a really nice thing about this. What is with the MAC address? For example, when I send out the frame to the router, what is in the MAC address? Is there a broadcast again? No. We have a special multicast address. It starts with 003333, and then the last part is taken from the IP address. So the 2 is taken over. We know this from the multicasts in IPv4. It's the same. We have the 224 at the beginning, and the last bytes are taken over. So let's look at the 16. So on a normal switch, this frame would still be sent to all the ports, right? Because the multicast bit is set in the destination. You see, the multicast bit is set. But just think a little ahead. These switches become more and more intelligent. So it would be an easy part to implement on which port of a switch the router is located. I mean, switches can learn MAC addresses. Newer switches even learn multicast addresses. So why not implement that the switch learns on which port the 02 is located and forward the frame only to that port? And then we would completely avoid that this multicast is sent to all ports. So I see an intermediate. You still can use a normal switch. By default, every switch is IPv6 ready. You don't need IPv6 feature on a switch, but there are already IPv6 features on switches. For example, there are switches which do not accept a router advertisement from any port. You can fake a router advertisement very easy, right? From a client. Newer switches like Cisco, they detect that the router advertisement from a client port is not accepted, things like this. So really a lot of potential here in this protocol. And we are going to see much more over the time. Yes, DHCP. Remember, the client may be allowed to fetch more data from a DHCP server if the other bit is set here or the full management bit is set. It works the same way. We have seen the multicast going out to the column 2, which is here hitting the router. We have to configure the relay address here. That's the command for a Cisco router. I just for fun took the cafe here just to make it a little bit more readable. You can now do some hex games with beef, dead beef, and so on. I've seen and so on, just to make it a little bit more readable. The router will then, like in IPv4, will make a directed frame. It has a different name. It's called relay forward. And it contains the source address of the router on this port, and it contains the destination address of the DHCP server, like we had it in v4, nothing special. And then the relay reply, and again the Cisco the router works then as a relay to forward these parameters to the client. So that's all really nicely decoded with Wireshark right from the beginning. That's really great stuff to learn how the protocol works. I really recommend do this test with your PC. That's why I did not provide the trace file. There are nothing special. And we have different behavior between Unix, Linux systems and Windows system, and even Windows keeps changing. So I would recommend do this with your environment and make a trace of your environment. It may look slightly different than what I'm showing here, and yes. Yes, of course, we have to, in order to communicate via IPv6, we also have to have a DNS server which is able to deliver us the IPv6 records. And they are called quad A records. Remember, in IPv4, we had the A record for address. And in order to make it easier, because the address is 4 times longer, they just call it quad A record. So if you want to communicate with a V6 server, you need an address which is, of course, IPv6. Most servers these days are dual stack, but you can even ask for a quad A record over IPv4. That is nothing to do. One is the transport protocol from the client to the server, and the other is the content. So both are valid, and you can find yourself what is done. Let's say the client only has an IPv4 DNS. It did not get an IPv6 DNS. It can still ask the IP over IPv4, can still ask the DNS for IPv6 records, and then start a communication with IPv6. So these are independent parts. Some providers still tunnel then over IPv4. My provider here in Switzerland, Swisscom, I have IPv6 already to my desk. My router provides me with an address and so on. So I have fully IPv6, but that depends on your provider. Some provider do tunneling and then unpack it somewhere. That's, of course, depending on what your provider is doing. So this is a screenshot for a query, a quad A record over IPv4. You still get a reply. And this is the same query over IPv6. You still get the same reply. So that's just no big issue here. Of course, the server has to be provided with all these addresses, of course. You have your new table, the pointer table, the reverse lookup, and the forward table, they have to be added, of course. But on the internet, this is no problem anymore. So let's look for the last thing. Let's look at the trace file, which I made just very recently for wireshark.org. I opened this one to see it real, because I found some amazing stuff in it. Okay. So you see, that's my workstation here. MAC address. My router is also my DNS proxy. So I send a request to the FE80 of my route. I don't use the public address of my local router, the 2000. So whatever is local will be used with FE80. I do a standard query, a record of Wireshark, and the quad A record. Most browsers these days, if they receive both values, they will prefer IPv6 over IPv4. So you can see this here. My browser received both addresses. Wireshark address, it takes the first one here with the 4B27 at the end, and then it sends out the TCP sync to that request. But then I looked a little bit further down, and thanks to this nice preview here, intelligent scroll bar, I realized, hey, what's going on here? It changes to QUIC. That's amazing. We heard it from Chris yesterday. Very interesting session about QUIC, and I'm also working on a QUIC course. They are changing on the fly to QUIC. I didn't even know that Wireshark is QUIC capable. You know it from all Google servers, YouTube and all, they can QUIC. I have changed my browser to allow QUIC. QUIC is standardized since 2 weeks, so it will soon be by default active. I had to manually activate it, but I was really surprised that it suddenly changes to QUIC. And then I wonder, how did it find out that Wireshark.org supports QUIC? And I started looking in some DNS here. Is there somewhere a hidden hint? No, I didn't find it there. But I found it after I installed my key here and decoded the frames. And that's the last thing I would like to show you. It's really interesting. What I have to do, I have to, of course, allow decoding of the TLS protocol, which I do here with protocol preferences. And then I have to add here the correct key. And unfortunately, my key, I didn't delete my key for a long time. So it's a really large key. So it takes about 3 minutes to open this file, but I should have cleared this key before this trace file. So it takes now quite a while to open this. In the meantime, I go further in the detail here. Yes, this is the QUIC reference which I showed you. Yes, how do you get ready with Wireshark, with IPv6? Yes, I mean, of course, you can ask your suppliers to support IPv6, which is really common these days. Unfortunately, IPv6 has a lot of options, and IPv-ready does not really define which options are used, so it's a little bit fuzzy what this label here means. You have to look into more details, especially on a switch. I mean, every switch can have this label. But as I mentioned, if you want to actually IPv6 for like router advertisement blocking and things like this, then it needs a little bit more than just switching. Yes, you can perfectly start with the running IPv4 network. So migration can really smoothly be done. Of course, maybe your router needs more memory because it certainly has to support two routing tables. So it's a good business for all router delivery. They need more memory for the routing table because you probably have to still support the IPv4 and so on. Here's some interesting links, and in the meantime, it should have opened my trace file. So now I can read. What's in, and then I looked here just before it changes to QUIC, and I found here in this frame here, I found a message that this site supports QUIC, and it is down here. It really took me a while under alternate services. Alternate services. And QUIC in common is not mentioned as QUIC, it's mentioned as H3, which stands for HTTP3, which is fixed bound to QUIC. And this is HTTP version 27 and so on. Then there's a max H timer 28 and 29. And to my knowledge, yes. So this we have now version 1. as the standard. So these have been pre-releases here in draft releases, but I guess in short notice there will be the QUIC version 1 here added to that list. So it's really nice to see that for some reason here the Wireshark.org delivers this header, and then the sender in the middle of the session moves and starts the initial of QUIC, and that's what we have seen with Chris here, the handshake, and it's based on UDP, of course. And it's quite hard to decode. We don't have acknowledges anymore like we have it in TCP. So I'm not looking forward to QUIC for troubleshooting. It will be a pain, but probably no way to come around. Okay.
Well, there's about 10 minutes left.
10 minutes left?
Yep.
Okay. Any questions left? Okay. Not so far. Yes. Let me see what else I could show you here. Yes, there is nothing special here. That's what we covered all. And yes, on my quick reference card, again, something which you have to learn new is the subnetting stuff. Again, do not use the 64 bits at the end for subnetting. It's not impossible. You can configure it, but we should, if we have the chance to get rid of the variable subnet mask, and we have the chance, then don't use it, because otherwise we have the same problem with IPv4. We never know what is the address and what is the network. So you have enough room in the first 64 bytes for subnet and network. Depends what company you are. If you are a big, large company, you may get from your provider a /32 prefix. That means you have then 16 bytes for subnet. That's 16 million subnet, right? 2 to the power of 32 of 16, yes. Maybe you get a /48. So these are the prefixes we are talking about. If you are a small enterprise, you may become a 48. You still have 16 bits, 65,000 subnets. And if you're not enough, you get another prefix. So it's absolutely no reason anymore not to use the 64 as the border. If you are a home user, you may get a 62 mask, still allows you with 2-bit and so on. So we have variable mask on the first 64 bits, but we don't have variable mask towards the network interface identifier. So that's the advantage we have now, because we have so much room left, so much space left. We can here really have a proper ID. Some people do concepts, they even built in the building number in this. They have so much room, they build in buildings numbers or whatever, or floor levels and so on. You have so much room left here. If you have 16 million subnet, you can play with these numbers and figures. There are a lot of different concepts out there which you can study. if you would like to make a concept. We can really start from scratch. We do not always have, like in IPv4, we do not always have to discuss how many IP addresses we need, how many network we need. We have just plenty of it. Okay. What else I have? Yes, here are the different address types. I mentioned this, the broadcast scopes, yes, anycast, multicast. That's more or less some display filters here. Neighbor discovery, the most important frames. The duplicate address test, we saw this. The one with the double column stand. Multi-listener query, yes, I mentioned that one. We are going to replacing IGMP, that means for multicasting. We are using these new commands, and the rest is more or less the same. There are a lot of tunneling techniques out there for IPv6, but I'm not explaining this. That's really different. Who is going to use which one? This is something you have to check on your side. Different commands for Linux, Unix, but it's just a couple of course. There's no room for all of them.
There is a question in the chat.
Okay. Where is the chat?
It's down below, but I can also read it if you want.
Yes.
About duplicate address. If it is derived of hardware, but only the last 3 octets are used, you could have to NIC.
That's a good question.
Okay,
I understand it, yes. Let's go back. Yes, that's a good point. I quickly explain what the question is. Where am I? Here. Okay. The question is, if in the duplicate address test only the last 3 bytes are checked, it could possibly happen that another station has the same last 3 bytes. Let's say we have 2 Wireshark 2 hardware Ethernet from one vendor, from a Dell and from an HP. They are different only in the first 3 bytes, right, in the vendor code. So they could, by chance, very small, but they could have the same last 3 byte similar. I don't know why they took the last 3 bytes. Unfortunately, a lot of the things are not really explained very good. But the problem is solved because the full address is in the hardware here. You see it here. You see the full address, which is going to be verified. So that's the point. But don't ask me why they took only the last 24-bit. I tried to find out why they took this strange pattern here, FFFA. No idea. I didn't find an explanation. There are too many things. I guess they had some thinking about it, but if you're not within these developers, it's not published why this pattern has been chosen. Yes. Any more question? This is valid. This is valid, of course, also for the public address. Again, in the public address, we are also using only the last 3 bytes, but if you look into it, then the full address is verified again. So if a station has the last 3 bytes, similar last 3 bytes, it would of course process this frame. All the others would discard it. But if you have by chance a station with the last 3 bytes, it would process, and then it would find out, no, that's not my address. And if it is, then of course it will reply anyway. And then the process has to repeat. Yes, any more questions? Yes, I see one in there. And some of the IP, okay. Some of the IP tunnel types have been deprecated over the last some years. Yes, that's true. I remember when I started my IPv6 first, I had an IP address for Teredo tunnel and all this stuff. This has gone in the meantime. So if you look at your if you look at your IP config, we only have one tunnel left. That's the isotap tunnel. Isotap tunnel allows to configure a tunnel through IP4 route. But we had Teredo tunnel and more here. They have removed this stuff. I guess you still could activate it, but it was there by default. Now it's gone. So this tunneling technology will go away, of course. The idea is to have one day a fully native IPv6 environment. That's, of course, the idea. Okay. Hope you learned something. And it would be a pleasure. I do trainings all over Europe. And if you have demand or another question, looking forward if you contact me. Thank you very much and have a good rest of the Shark Fest.